Thank you, and thanks, John. For those of you who haven't seen my talk yesterday, so I'm Julia Scharrichter, I'm based at Gemini North, and today I have the pleasure to talk about a research project I've been involved in for the last several years, which is the Close AGN Reference Survey, or CARS, for which we have also an ongoing project to obtain NIFS follow-up data. So the previous talk was a very nice introduction, of course, also to the NIFS capabilities and somewhat the data I will show in this talk. So this talk is in collaboration with the CARS team, and I would just like to acknowledge the past PI, Bernd Husemann, who has been leading the project for many years while at the MPIA, and our current PI, Rebecca McElroy, who is based in Australia. So the primary objective of the CARS survey is to really look into the details of AGN feedback by using a multi-wavelength approach and also a spatially resolved approach using IFU data. And since it's a bit more of a broader audience, I thought I would spend a few very basic words on what actually AGN feedback is. It's basically the cycle you have in a galaxy driven by accretion from the galaxy onto the supermassive black hole, which could then trigger star formation, grow the black hole, but also ignite an AGN, for example, basically through the conversion of mass into energy. And this energy release in turn can have an effect back on the host galaxy, and the primary processes discussed here are photoionization and heating of the interstellar medium in the galaxy. Feedback can also happen through radiation pressure-driven winds and outflows from the AGN, or through mechanical feedback from jets launched by the AGN. And AGN feedback has become a very integral part of our nowadays understanding of galaxy evolution. However, the observational details of how such feedback works are still controversial, especially on the observational side. And there are some open questions I'm listing here, which are also part of what the CARS survey tries to tackle, which include, for example, over which temporal and spatial scales do such feedback processes operate? Second question is, do AGN suppress star formation in the host galaxies, which has been suggested theoretically, but it's still observationally quite controversial. And the final question is also, how does AGN feedback actually couple to the multi-phase gas in these galaxies? And particularly, just looking at a single gas phase has been shown to not be sufficient to fully understand the impact of AGN feedback on a host galaxy. And there have been, of course, studies, for example, using multi-wavelength surveys to use multi-gas phases in the low redshift universe. The advantage of such studies, of course, is that there is sufficiently good spatial resolution to study really in detail the physics that's going on. However, such surveys are often limited to more lower luminosity AGN because they are studying the low redshift universe, which may not be fully representative of the conditions in the higher redshift universe, and also sometimes limited to a more specific AGN parameter space. On the contrary, looking at surveys in the higher redshift universe, you can probe the AGN luminosities that are more representative of the high redshift conditions where we expect major feedback to happen. However, of course, at higher redshift, the spatial resolution is somewhat more limited to really look into the physics in more detail. So CARS has been attempting to some extent to bridge this gap by looking into some of the most luminous unobscured AGN in the nearby universe. And specifically, the CARS sample has been selected from a parent sample of 99 unobscured AGNs, which are taken from the Hamburg ESO Bright Quasar survey. And these data were selected by using a redshift cut of 0.06. So these are really relatively nearby objects, but still quite luminous. And also we implied selection based on having already single dish CO data available for these targets based on a paper from Bertram et al. So the final CARS sample itself is a selection of 41 sources that were randomly taken from this parent sample of 99 sources. And you can see a gallery of these targets on the right, of the host galaxies on the right. And these data are primarily reconstructed images from Muse data cubes, and a few of these images are also taken from pan-stars. So I've already mentioned Muse has been at the core of the CARS survey, Muse at VLT. Specifically, the backbone of the CARS survey is the optical integral field spectroscopy, which was for most of these targets obtained with Muse at the VLT, and for 4 targets that were also added from observations with PMAS at Calar Alto and VMOS at the VLT. And of course, since I'm talking about a multi-wavelength follow-up, there has also been a larger campaign to follow up sources with the VLA, ALMA, Sophia, Chandra, and MIPS at Gemini, which is the part I will talk more about in a bit. And I should also mention that the spatial resolution, just for reference, of the optical IFU spectroscopy is somewhat variable by target, but in the very best cases, we achieved spatial resolutions of 0.4 arcseconds. And in the very worst cases, I think that's one of the PMAS data sets, we achieved spatial resolution of 1.7 arcseconds. So most of the data are somewhere around 0.6 to 1.2 arcseconds. And these were obtained with the Muse wide field mode. So, and before coming to NIFS data, I just want to briefly advertise also the CARS first data release, which happened recently. You can access that under this link here. The first data release includes the optical IFU cubes, plus some higher level data products, which were associated with 3 papers that were published with the data release. And I invite you to take a look at these, just showing a gallery of some of the plots included in the data release. One other aspect I wanted to mention is that the major goal of the CARS survey has been to employ an AGN host galaxy deblending technique on the optical IFU data, which is of course important to study in more detail the host galaxy's properties against the bright AGN. And this is done based on a PSF that can be traced in the cubes themselves by using, because these are unobscured AGN, by using the broadline emission from the broadline region of the AGN, which is intrinsically unresolved in this data, to probe the PSF and then perform an iterative host galaxy AGN deblending on this data cubes. And this is included in the data release. So now I will switch to the NIFS follow-up project and the primary goals. And again, thanks for the introduction in the previous talk. The primary goals were to add basically another multi-phase gas tracer, which is the warm hot molecular gas traced via the H2 lines in the near-infrared K band. And this is gas which is basically at a few thousand kelvins. And then to combine this with other gas tracers, for example, we were also interested in the iron 2 emission, which can be a tracer of fast shocks. And to combine this also with the larger multi-wavelength data we have available through CARS, especially the Muse and ALMA data and also VLA, to look for outflows in the multi-phase data. And finally, also we can take advantage of the reduced dust extinction in the near-infrared to combine, for example, what we know about star formation from the Muse H-alpha data with information we may get from the hydrogen recombination lines in the near-infrared data, especially in this case, Paschen beta and bracket gamma for the wavelengths we have been covering. So far we have 4 sources that were fully observed in the 2 bands we had requested, plus 2 sources that were are partially complete in the K bands. And I should also mention that, of course, we wanted to achieve reasonably high resolution. So for the K band, almost, I think, except one data set were observed with adaptive optics through Altair. In the J band, we had been relying on good natural seeing. For the Gemini term, it's IQ 20 in most of these cases. So that is complementary, but somewhat worse than the adaptive optics data we have obtained in the K band. So one very interesting target from the CARS survey, which had been actually followed up with NIFS with an FT program, and really shows the power of combining the multi-phase data we have within cars is this source HE1353, which in the MUSE data revealed a very extended ionization cone, which you can see in the green data in the 3-color image from MUSE on the left. The green color here traces the O3 emission. So this was anyway an interesting source because it's an unobscured AGN, but still seen in a relatively edge-on galaxy from our point of view, which means that there is quite likely some major effect from the AGN onto the host galaxy. So this ionization cone, based on our interpretation, is not an AGN outflow, but it's probably gas that was uplifted from the disk through star formation processes and then illuminated by the AGN. However, interestingly, we also see now looking at, if you can see that the VLA contours in blue overlaid on the ALMA image, you can see that there is an extension in the VLA contours, which may suggest an AGN jet. And we have been focusing into that region with NIFS, which is the field of view shown in yellow here. And the NIFS data, interestingly, shows that all of the emission lines we have been detecting, RN2 was a bit faint to detect, but the bracket gamma, Persian beta, and H2 lines show like 2 off-nuclear emission peaks, which are about 0.6 kiloparsecs from the nucleus. And interestingly, the southwestern peak particularly aligns with where we see this elongation in the radio contours. So there might be some jet-driven interaction scenario, which is further supported by the kinematics, which can be seen in the lower left, which shows that there is a gradient in kinematics through the southern emission peak, which might indicate some driving of gas through mechanical interaction with the radio jet. Now, combining the NIFS data with the multi-phase gas tracers, you can now see velocity dispersion maps for the O3 ionized gas from MUSE on the left, and for the cold molecular gas and CO120 from ALMA on the right, compared to where we saw the emission peaks in the warm molecular gas from NIFS. It's interesting to note that all of these, that these 2 other gas tracers show higher velocity dispersion in the same region, which really, and also not showing here, but they also have broader line wings in this area, which really indicates that we see possibly a radio jet driving a fast outflow in the circumnuclear 1 kiloparsec region of this galaxy by interacting with the dense molecular gas in this host galaxy. So just for the last few minutes, I'll just take you through some of the work in progress with the other NIFS data, just to show you the NIFS data quality and what we are working on. This is another galaxy from the CAR survey that was followed up with NIFS, HE2302. And you can see this is a rather disk-dominated galaxy, which has a disk rotation. So on the left, you see the H-alpha surface density, O3 surface density, gas velocity, and gas dispersion from MUSE. In the full MUSE field of view, which contains basically the whole galaxy in all of these cases. And now zooming into the center of the MUSE data, and I'm comparing this now again with the NIFS field of view we can get in the black square. You can see that NIFS now shows the center at a much better resolution. It's about a factor of 3 for the K-band data, which were obtained at a higher spatial resolution. And this shows that all of the lines we have been seeing here show some evidence of a nuclear spiral. And especially looking at the H2, the gas kinematics is somewhat matching what we see in MUSE. The gas velocity dispersion is relatively small, so probably this galaxy shows more like an accretion tracer through the H2. And I should mention that all of these NIFS data are somewhat preliminary in the sense that we are still working on a similar AGN host decomposition for these data, which should much enhance the contrast versus the nuclear PSF on what we see in the more extended gas distribution. A very different source is this source, HE0232, which is a very interesting ring-shaped galaxy, which is known to be a merger candidate with a double nucleus. And you can actually see the second nucleus next to the AGN in the MUSE image. It's about 3 arcsecond from the AGN center. And this galaxy has a very complex kinematics, especially if we zoom again into the center. You can see that, of course, in the double nuclear region, both the gas velocity and gas dispersion are very complex. And then again, I show here the preliminary NIFS data, where we see also very extended gas emission with a similarly complex kinematics, and the analysis together with the MUSE and VLA data is now, especially with respect to the kinematics, is now ongoing. So I'll just conclude by saying that the restful near-infrared IFU observations of nearby AGN play an important role in really tracing the multi-phase gas in the vicinity of an AGN, and this is true for cars, but also there have been many studies using, for example, also Symphony, NIFS, and OSIRIS. And we have already preempted a little bit this discussion in the previous talk. I also wanted to mention that this will also be an important science case in the near-term future, of course, for the GENIUS high and low-resolution IFUs, and also in the longer term, coming back to my talk yesterday, for the capabilities Gemini North will offer with the new AO system, GNAO, and GearMOS, which is also a near-infrared multi-object IFU. Thank you.
Thank you, Julia. Okay. Are there any questions from Slack? No. 1 minute. So I guess the CARS survey has a very good job on the PSF subtraction. And can you comment on the high Z IFU studies where it's very much more difficult to do PSF subtraction?
I think, well, the advantage we have in the CARS survey, of course, is that we have a very clear detection of the broadline region where we can really use this as a tracer of the point source through the cube itself. So I think this is, I mean, I'm not a very good expert in the high Z studies, but I think this is more of an issue for the high Z studies, especially if you don't have a PSF tracer in the cubes themselves. So you may need a PSF reference separately observed, which then complicates things compared to these pretty high signal to noise near data we have. So this is also, of course, an advantage, again, that we can really use the higher spatial resolution and the better contrast after AGN host subtraction to study the host galaxy gas near the AGN.
Thank you. Any other question? If not, then let's thank the speaker one more time. Thanks.